LLM as Dataset Analyst is a project done by Yulan Luo, Ruichuanen, and others from Peking University. This research explores how large language models can analyze dataset characteristics and assist with classic machine learning tasks. A subpopulation is a group of data samples with shared characteristics. The concept is related to various tasks. For example, ECCV is an image clustering task based on user-specified text criteria. Subpopulation shift occurs when the proportion of some subpopulations between training and deployment changes, leading to significant decreased performance. In traditional data-centric machine learning, slice discovery focuses on finding and summarizing subpopulation, or slices, within a dataset. These slices are subsets of data with shared characteristics where the model performs poorly. After analyzing these tasks, we realized that understanding subpopulation structures can significantly improve them. For user-customized text clustering, we can match user-provided text with known subpopulation semantics to find the best fitting group, giving a clustering result that meets user needs. To address subpopulation shift, we can analyze subpopulation distribution and adjust for the long-tail effect using retrieved or generated data. For slice discovery, we test each subpopulation separately. A slice is identified if its error rate is much higher than average. Despite the significance of understanding the data, existing studies lack of systematic exploration into the distribution of subpopulations within datasets. To address the gap, our research makes several key contributions as following. Next, we will introduce our method from the aspects of subpopulation structure definition, significance, type, automatic discovery, and downstream task application. The first comes the definition. Subpopulation structure refers to a set of layered relationships among different subgroups within a dataset, defined by certain criteria. By discovering and examining these structures, we gain a clearer understanding of the dataset as a whole. This understanding helps us tackle problems related to these subpopulations in a data-centric way. Given that subpopulation structures are significant, we need to discuss what constitutes a good subpopulation structure. Metashift and Nico++ proposed various methods to divide datasets, such as categorizing by objects or backgrounds. However, these approaches have some limitations. The understanding of the dataset is not comprehensive enough. There are overlaps between attributes, for example, dog and surfboard or dog and water. Upon mentioned drawbacks highlight the need for more refined approaches to creating effective subpopulation structures. A robust subpopulation structure effectively organizes and clarifies relationships within a dataset. The current baseline categorizes data into 3 layers: class, attributes, and subpopulations. To improve clarity and understanding, we propose an advanced 4-layer structure. This new framework adds a dimension layer between class and attributes, providing a more detailed and precise representation of the dataset structure. Now that we've clarified what a good structure looks like, we need to know how to get this structure. Traditionally, scientists manually summarize results, but the scale of modern data and specialization complicates this process, so an automated framework is necessary. In this work, we achieve this by utilizing LLM and MLLM. We use MLLM to translate information from images and leverage LLM's world knowledge to better understand the entire dataset. Specifically, our framework consists of 4 steps. First, we use MLLM to extract detailed captions from images. Next, LLM generates potential dimensions and attributes from these captions, establishing the initial criteria for analysis. The third step refines these criteria through an iterative process using a single caption sample to classify results for consistency and precise. Finally, refined criteria assign captions to specific attributes, organizing the dataset structure. This pipeline allows for further task-specific tuning, facilitating downstream subpopulation-related tasks. So the final problem to be solved lies on that how to elegantly apply subpopulation structure to downstream tasks. For unsupervised clustering, the approach uses subpopulation structure to organize image datasets. It employs SSD-LLM to extract attribute dimensions and attach them to images. Combined with image generation, this helps manage subpopulation shifts. We gather statistics on image numbers in each subpopulation and use diffusion models to generate images for underrepresented groups, balancing classes and attributes. Finally, the method identifies high error rate subpopulations and uses LLM to summarize their attributes, uncovering key data slices. This is the visualization of our organized dataset. You can see that the text matches the images well, and the text criteria are more fine-grained. We perform user-customized clustering on multiple datasets, achieving better results than the traditional scan algorithm and the recent ECCV method. The table shows quantitative results for dataset subpopulation organization. A higher score indicates better clustering performance. In our experiments on subpopulation shift, we compared our approach with various data-centric and model-centric methods. We achieved impressive SOTA results. The table compares methods for image classification under subpopulation shifts, where higher metrics indicate better performance. We redesigned the slice discovery evaluation pipeline to assess the algorithm's ability to identify error samples. A higher error rate in identified topics indicates better performance. Our method outperformed the classic domino algorithm in recent studies. These are our conclusions and potential future work of our research. In summary, we explore large language models as dataset analysts to extract insights that improve model training. We also introduce subpopulation structure, a framework for analyzing dataset subpopulations and addressing challenges like shifts, organization, and slice discovery.